Hi, welcome to the next in our series of Practical Electromagnetics for Engineers. Today we're going to be talking about the polarization of electromagnetic waves, or the polarization of plane waves. If you're in my class, you can go ahead and study along in section 7.3 of your textbook, but my derivation is going to be a little bit different and hopefully a little bit more intuitive. Well, you see in a lot of textbooks pictures of plane waves that look something like this, and we know the equation for a plane wave is given by the electric field as a function of z and t. If we sort of simplify and assume things are the wave is propagating along the z-axis, looks like this. And we also know it's very hard to express a wave in both frequency and time in a static two-dimensional diagram like you might find in your textbook here. What we want to talk about today is the polarization of a wave, and essentially what polarization is the direction the electric field points as a function of space and time. And you know, we typically think of the electric field pointing as one direction, but in fact the electric field vector direction can change in space and time. And so let's see how that works. We know with our plane wave solution that at any point on the wave, say right here, I've chosen a positive going peak, that in the direction orthogonal to the direction of propagation, which is the xy axis here because the z-axis is the way the wave's going, that the electric field is going to have a constant value. And we know this as E naught, and essentially it's going to be a vector. And so we can draw a vector field on top of this point, and basically we're saying, okay, the electric field of this wave points in the plus x and the plus y direction from the way I drew this. And we know from vector fields that essentially it's going to map a vector onto every single point of space. Now you don't see this drawn in textbooks very much because it's very, very hard to represent this in a static diagram. At some later point in space, let's say where the wave crosses zero right there, there's going to be no field at all, and that's represented by this blue plane here. There are no vectors here because the value of the electric field is zero, and so the vector field is uniformly zero everywhere. If we go to essentially one of the negative peaks of the waves, right here, we know we're going to have a value. The electric field is going to have a negative value here because that's the negative part of the wave. And so we can express our vector field as simply pointing in the opposite direction. You'll notice the arrows on the positive plane and the negative plane simply point in the opposite direction. So we get this picture as the wave is moving through space as a vector field that sort of changes direction. And of course the vectors won't always have the same length. At some point right here where the wave has a positive but not the peak value, you're going to get a vector field, but those vectors are going to be shorter than in the case over here. So again, it can be very hard to sort of get a mental picture of how these plane waves move. So the topic for today is polarization, and essentially polarization is just the term we use for the direction the electric field vector points. And because this wave is changing in space and time, the electric field vector may point in different directions as a function of space and time. And that's what polarization describes. In the diagram I've drawn right here, notice I've drawn my electric field vector going up and down. So the direction of polarization is in the y direction because E points in the y direction no matter where I go in space. You might say, gosh, it may be point in the negative y direction at this point in time and the positive y direction at that point in time, but nevertheless we call it polarized along the y direction. The magnetic field, of course, for this wave is polarized along the x direction because it's orthogonal to the magnetic field and orthogonal to the direction of propagation, which we've defined to be z. So we essentially see that we can talk about E-plane polarization in this diagram as being the YZ plane. It's the plane in which the polarization lies. The H-plane polarization is essentially the XZ plane here because that's the plane in which the magnetic field lies, no matter how we propagate along the wave. And so one of the terminologies used in electromagnetics is we talk about E-plane and H-plane polarized waves, where the plane that contains the electric field is the E-plane, the plane that contains the magnetic field is the H-plane. Pretty simple. Things get a little bit more complicated, of course, in the case that my electric field vector isn't along either the x or the y axis. Here I've drawn a case where the electric field vector points in both the x and the y direction. And this next part is the really important part about understanding polarization. If you get this idea, then polarization makes a lot of sense. Otherwise it can get very complicated. And the key idea here is that you can essentially superimpose waves. Remember, our principle of superposition said we could build up the overall electric field or overall magnetic field from a sum of individual electric fields that originated from different points in space. This is why you had all those integrals when you were doing electrostatics. Well, because plane waves are just oscillating electric and magnetic fields, it turns out we can build any type of plane wave from the summation of different components. So the way you think about this electric field vector or electric field polarization that's not either an X or Y is you sort of take this diagram, rotate it 90 degrees so the z-axis is pointing out of the screen at you, and that's going to be this diagram here. So essentially now if you think of the z-axis coming out of the screen, we have the x direction going this way, the y direction going that way. And you can see here that we can represent the overall electric field vector, E, which is that green line, as the sum of two components, an electric field vector in the y direction and an electric field vector in the x. And this is a really important point, and it's worth repeating. I can take any electric field and represent it as the sum of multiple electric fields. That's the principle of superposition. So essentially what we can do is we can say this green line that's essentially oscillating in the xy plane is exactly equivalent to saying we have the summation of an x-going field, that's the red wave here, and a y-going field, which is the blue wave. And I'm going to use red for x and blue for y and green for the summation of x and y throughout all the rest of this mini lecture. So again, let me say that these two things are equal to each other. They're simply different mathematical representations of the same thing. And so the key point here is because superposition holds for electric and magnetic fields, as long as we're in the linear case, that we can essentially make an overall plane wave as a sum of individual components. We can also take any plane wave, no matter what direction the electric field is, and subdivide it into two or more different components. And that's what allowed us to take this green field that's pointing in the xy direction, so at some maybe angle theta to the x-axis here, and represent it as a sum of an x component plus a y component, as shown down in this diagram down here. So at this point, once you get this idea of superposition, that you can take any wave and break it down into components, we can begin to understand polarization in a much more formal sense. And what I'm going to do is I'm going to develop essentially more and more complicated pieces and build this up piece by piece in order that you can understand it a little bit better. So the simplest case we're going to call case 1a is what we call linear polarization. We only have one component of the electric field, and that's shown in this diagram here. Essentially the electric field simply points along the x direction. I could have equally said it points along the y direction, and the way I would mathematically represent this plane wave is as follows. There's an electric field vector that's a function of x, y, z, and t, and that's essentially given by this expression here. You have the magnitude of the field pointing in the x direction, varying sinusoidally both in time and in space. And of course there's no component in the y direction the way I drew this right here. Now in order to understand this better, what I want to do is I want to insert a little narrated video I made from a MATLAB animation I did of a plane wave varying only in the x direction. And so essentially the plane wave you're going to see in the next video corresponds to this case, which is our simplified diagram, and was generated by this formula right here. This is an example of an electric field moving in the x direction. You can see it simply oscillates back and forth in x and propagates along the z-axis. Here we simply have one component of the electric field, giving rise to a linearly polarized wave. Hopefully that video clarified essentially what a plane wave might look like that's varying in space and time. I couldn't capture in MATLAB the fact that we're creating a vector field at every point in space, but you got the idea of this wave that had an electric field vector that oscillates in the x direction. As we look at more and more complicated cases, case 1b is going to be a linearly polarized wave, but essentially we're going to have two electric field vector components. And again, this is the case we looked at differently. We essentially have some electric field vector E that's not pointing in x or y direction, but at some angle to the x-axis. We can represent this as the sum of two components, an x component and a y component. Here's my x component right here. It looks exactly the same as above, except now I have some amplitude in the x direction, and I also in this case don't have a zero y component, but I have some y component that has an amplitude EY. And these two values need not be equal to one another. And in fact the relative ratio between EX and EY is going to determine the direction the electric field points, or alternatively the angle theta, because of course we know that the tangent of theta is simply going to be E y over the value in the x direction. So let's stop and take a look at a video of what linear polarization looks like, where I'm going to have two components. Essentially, the y component is a blue line, the x component is a red line, and the overall electric field, which is going to be the sum of those two components, is a green line. This is a case of linear polarization where both the x and the y components are oscillating in phase, red x, blue y, as you can see, and you'll see that although the wave's at an angle, the polarization is linear. It still just makes a line as it propagates through space. Hopefully that video really clarified what was going on, so you can see the wave moving in both space and time. Now, of course, things can get more complicated still, so the next case we're going to talk about is something called circular polarization. This is when you have two equal components of the electric field, but there's a 90-degree phase difference between the components. So let's see what that looks like. Essentially, we start off with an x component of the electric field. We know we have a y component, but since it's 90 degrees out of phase, when the x component is maximum, the y component is 0. As we go to the next point in time, and so let's call this t equals 0. As we sort of go to the next point in time, t equals 1, because these are sinusoidal waves, the x component is shrinking, it's getting smaller, and the y component is growing, it's getting bigger. So if you actually look at the overall direction of the electric field vector, it's essentially starting to move and rotate in the counterclockwise direction. At some other point in time, let's call it t equal to 3, our x component has shrunk to 0, it's at the 0 of its sinusoidal motion, and the y component has grown to its maximum value. So essentially what you see over time is, if you animate this, you're going to see the electric field vector making a circle in the counterclockwise direction. The way we represent this mathematically is pretty simple. We know that the x and y components are equal, so we just set the same amplitude for both of those. Here we have the x going phase, and the y going phase is the same. It varies with time and space, but it's 90 degrees out of phase, or pi over 2 radians out of phase with the y component. So let's stop and insert a video that shows this circular polarization. This is what happens when we have two components that are 90 degrees out of phase. The x component is red, the y component is blue. It's called circular polarization because the overall green field vector, as you can see, makes a circle, and the wave itself sort of corkscrews as it propagates through space along the z-axis. Hopefully that really clarified what was going on in this case, and you can see as the wave moves in space and time, it makes this strange corkscrew motion. In this case, for circular polarization, you really see the direction of the electric field vector is different as a function of space and time. Let's take a look at the next most complicated case, which is just another case of circular polarization. But in this case, we say the phase difference is negative 90 degrees rather than positive 90 degrees of the case above. Again, we start off at time t equals 0 with the electric field vector in the x direction. However, as this vector shrinks, the y vector is going to grow in the negative direction because of the phase difference. And so now essentially what you see is instead of a counterclockwise rotation, you're going to get a clockwise rotation of the vector. Again, exactly the same formula as before, equal amplitudes, but now we have a negative 90 degree or negative pi over 2 radian phase difference. Let's stop and take a look at a quick video of what circular polarization rotating the other direction looks like when we simply change the phase difference. This is the opposite case of circular polarization with a 90-degree phase shift between the x and y components. You can see that the wave simply corkscrews in the opposite direction, but the overall resultant electric field vector still makes out a circle as the wave moves through space. The final case I want to look at is known as elliptical polarization. This is the most general case. In this case, the x and y components of the vector are unequal, they're not the same, and the phase difference is something other than 0 or 90 degrees. Essentially, in this case, what happens is you have an x component, over time a y component grows, and you get a rotation of the vector. But as we'll see in the video, instead of drawing a circle, because x and y are equal, because in this case x and y have different values, it creates an elliptical shape, and hence it's called elliptical polarization. And there's a phase difference between x and y that's not 0, and this phase difference and the difference between the amplitudes of x and y is going to determine the shape of the ellipse. So let's stop, take a look at a quick video for the most general case of elliptical polarization. Again, remember, this all arises from simply breaking down our electric field into two different components, an X component and a Y component, and saying there's a phase difference between these. So here's the video. The last case is elliptical polarization, where we have unequal X and Y components, and the phase difference is not 0 degrees. It's called elliptical polarization because the overall vector traces out an ellipse, and you see there's sort of a skewed corkscrew as the wave moves through space. You're probably getting a little bit bored of these videos because it should be fairly obvious, but you can see why we call it elliptical polarization, because that green electric field vector traces out the ellipse as it moves over the XY plane. Now, this isn't really covered in your book, but I'd like to talk about what happens when you have more than two components. In other words, you sum up a whole bunch of electric fields rather than just two that are pointing in different direction. And this brings us to the topic of coherence. Coherence has to do with the phase relationship of multiple waves. And remember, this is our expression for phase. Generally, we have a time component and a spatial component. If we look at the time coherence of phase, and let's say we're going to sum up three different waves. Let's call it wave 1, wave 2, and at the bottom here, wave 3. Essentially, you can see that I've set up these three waves so that they all have the same phase. They add together in time. And so if I have multiple waves that have some kind of known phase relationship, then essentially they're going to sum up proportional to the number of waves, which makes sense. If each of these waves has an amplitude of 1, the overall amplitude of this wave, you can see, would be 3 due to linear superposition. So the amplitude of the overall wave for coherent waves scales as the number of waves you sum. However, nothing says that I have to have all the waves be in phase, the waves that I sum up be in phase. And here, in this case down here, we have the three waves, but they're not in phase. There's some random relationship between the phase of wave 1, wave 2, and wave 3. In this case, as I start to find the amplitude of a sum of a bunch of waves that have random phase relationships, I find the overall amplitude sums the square root of the number of waves I sum up. The idea of coherence also applies not just to time, but to space. And the idea of spatial coherence is that if I have some kind of emitter, and I'm going to use some sort of radio dish as my emitter here, that at different points on this, the waves, and I've summed up 4 waves here, have some kind of coherent phase relationship. In this case, if I sum the waves over space, essentially what I'm going to see is the amplitude is going to sum again as the number of waves. For an incoherent source, such as something like a light bulb, waves come off the filament at different points in space, but the relationship between the phase of those waves at each point of the filament in a light bulb is random. It's incoherent. And in this case, the wave sum is the square root of n, just as in the time case. So we've introduced the idea of summing lots and lots of waves that can sum up either coherently, linearly with the number of waves, or incoherently as the square root of the number of waves. We've already talked a little bit about some of the conventions we use in polarization, and it's important to understand the language people use when they're talking about polarization. And we found that we can term in electromagnetics polarization is either E-plane or H-plane, depending on which plane contains the electric field and which plane contains the magnetic field. Other notations of polarization have to do with the definition of what's called a plane of incidence. And this is what happens when an electromagnetic wave interacts with an object. And I've drawn a planar object here, basically just a surface. And essentially what I'm doing is I'm defining the direction of propagation k of my k vector coming in here, and the normal to the surface in. Because remember, any surface is defined in a direction by its normal. And the plane of incidence is the plane which contains both the incident vector of the electromagnetic wave and the surface normal. And I've basically represented the plane of incidence as a gray plane right here in the diagram. So if we have a situation where a wave that's polarized in some direction is coming into a surface, and the electric field vector is perpendicular to this plane of incidence, we call it S-polarization or perpendicular polarization. And S we can think of as a slapping polarization, because that wave comes along and just hits it flat on like a slap. In the case, on the other hand, where the electric field vector lies in the plane of incidence, and that's shown in the case down here. Notice our electric field vector is in the gray plane rather than sticking up and down from it. We call it P, and this word should not be slapping. It should be piercing polarization. That's why it's called p-polarization, or parallel polarization, because that electric field vector is parallel to the plane of incidence. So again, E plane, H plane, S or perpendicular, P or parallel polarizations are all terminologies that are used when you're talking about polarization of waves, and we're going to come back to this later on when we talk about how waves reflect off of surfaces. I'd like to end this lecture with a very brief discussion of polarization components, and there are a lot of different devices out there that will change or modify the polarization of waves, but I want to talk about one that's used in electromagnetics a lot, which is a wire grid polarizer, because it's fairly easy to understand. And a wire grid polarizer is exactly what it sounds like. It's essentially a grid of wires. So here you have some kind of wires. There are these gray cylinders, and they're conducting. They're wires. They conduct electricity very well. So we say the conductivity is much greater than 1. For a wire grid polarizer to work, the spacing, horizontal spacing between these wires needs to be much, much less than a wavelength. Otherwise it doesn't act as a polarizer. And also the length of the wires, the size of the polarizer in this vertical direction, needs to be much, much greater than a wavelength. And if you construct something like this, you've essentially made a wire grid polarizer. So how does this thing work? Well, if you have an electric field that's polarized here in the vertical direction, it's going to come along, and that electric field, because J is equal to sigma E, E is going to induce a current in the wires. So all of those electrons are going to feel the force of the electric field, and they're going to go rushing in the direction the electric field points. Well, because it's an oscillating electric field, the electrons go up, they go down, they go up, they go down, and essentially just oscillate within those wires. Now, it takes energy from the wave to move those electrons, to accelerate them, to push them up, and then to change their direction and put them down. And so all the energy of the electric field goes into pushing those electrons. And so no electric field gets through this wire grid polarizer because those electrons are going up and down. Well, let's look at the case that the electric field is essentially perpendicular to the wires, as shown here. In this case, the electric field tries to accelerate the electrons, but they really have nowhere to go because these wires are so much smaller than the wavelength. They're essentially fixed in space. The electrons can't be pushed around by the field, and so very little energy of the electric field goes into moving the electrons, and so this is transparent to electric fields in that direction and opaque to electric fields in that direction. So what this essentially means is that if I put this in front of a beam of radiation that's not linearly polarized, what comes out on the other side of the wire grid polarizer is going to be linearly polarized, and it's going to be polarized in that direction, orthogonal to the direction of the wires. That wraps up polarization. Hopefully you understand this simply as superposition of two different x and y components of a wave with various amplitudes or various phases. We just attach names to it. The idea is really simple if you get the idea of any wave being able to be written as the sum of two different components.